the digital processing of analog signals. Whenever we want to process any signal, the first...
You're watching Electrical Engineering Lectures channel. For more videos, please do like, subscribe, and hit the bell icon for the latest notifications.
Assalamu alaikum everyone. In today's lecture of digital signal processing, we will be discussing digital processing of analog signals. First of all, we will discuss the theoretical concept behind the digital processing of analog signals. Whenever we want to process any signal, the first step that we need to take is the conversion of the analog signal into discrete. So by using C to D converter, which uses a sampling period of capital T, we first of all convert the continuous time signal into discrete time shown by x of n, and then we process the filtering or any kind of processing on this x of n to produce the output signal y of n. So this block is the main core which includes any kind of processing that we need to perform on the input signal x of n. After the processing, we need to convert the discrete time output y of n back to continuous time by using the same sampling period which was used in C to D conversion to generate the final reconstructed output yr of t. Now, what are the problems in this approach? The first problem is that usually due to some hardware constraints, we require lower sampling rates to reduce arithmetic processing, and secondly to reduce the number of samples to be processed, because the lower the sampling rate, the lower will be the number of samples that need to be processed in the second block, which was discrete time processing. So due to this reason, we usually want the sampling rates to be on the lower side. But what is the problem in achieving lower sampling rates? The problem is that the analog signals are usually not band limited. The bandwidths of the analog signals are usually very high, approaches to infinity, and due to those higher bandwidths, as per Nyquist criteria, sampling rates are usually very high. But to avoid this problem, what we need to do, we need to perform pre-filtering. By performing pre-filtering, we can reduce the bandwidth of the analog signals having higher bandwidths to lower bandwidths. And when the bandwidth is reduced, of course at loss of certain amount of data, but in order to have lower sampling rate, we need to reduce the bandwidth. And how can we reduce? By using pre-filtering. And this problem is inherent, the problem of higher bandwidths is inherent in both the narrowband and wideband signals. For example, let me show you an example of the speech signal. If we plot the speech signal in frequency domain, speech signal, if I plot the spectrum, let's say x of f of that particular signal, it is roughly having a shape like this. So this particular signal has very low contribution around DC, and also it has a very limited contribution above a certain frequency, which is usually 4 kHz. So above this 4 kHz frequency, the signal contribution is very low. So due to this reason, if we simply perform a filtering over here to reduce the maximum frequency of the signal, then the sampling rate, which must be at least 2 times the maximum frequency of the signal, that can be definitely reduced. Similarly, in case of wideband signals, especially if we talk about communication where we convert a baseband signal to a passband signal, let's say we have a carrier frequency FC of 100 megahertz here and minus FC over here. So the signals are usually like this, having certain amount of noise on both the right and left hand side. So if we want to sample this signal at twice the maximum frequency, then definitely the sampling rates would be very high. For example, in this particular case, let's say I say that this frequency is 110 megahertz. It means at least I need to have sampling frequency of greater than or equal to 220 megahertz. which is definitely a very high sampling rate. We will not want to have sampling rates as much high as this 220 megahertz or something like that. So due to this reason, we usually filter the analog signals prior to the C to D conversion. This is called pre-filtering, or we also call it as anti-aliasing filter, because it is used to avoid the anti-aliasing by reducing the sampling rates. So due to this reason, this kind of filtering is called anti-aliasing filter. So these are some examples that how and why we need to perform pre-filtering before C to D conversion, right? So another aspect of this discussion is also that usually in practical systems, we perform a reverse approach. Given the hardware constraints and given the capabilities of the platforms on which we are going to implement some signal processing algorithms, we usually first of all decide the sampling rate, and then after fixing the sampling rate, we usually find out what maximum frequency that we can have of the analog signal in order to avoid aliasing. For example, and for some hardware or for some platform or for some constraints, I decide sampling rate to be 1 megahertz at max. So it means I can only afford the maximum frequency of the analog signal to be 500 kilohertz. The maximum frequency cannot exceed 500 kilohertz. If it exceeds, it means there will be aliasing. So I will design a filter, an anti-aliasing filter, so that it minimizes or it reduces the maximum frequency of the signal by filtering to 500 kilohertz. So that is called a reverse approach. So this anti-aliasing filter must be definitely in analog domain, because it is filtering the continuous time signal which is coming at the input of C to D converter. So this is point number one. And secondly, this must be a low pass filter, right? So this filter is called anti-aliasing filter, and ideally the frequency response of anti-aliasing filter is given by this particular expression, that if we want to cut the analog signal up to omega c, a certain frequency, then this anti-aliasing filter ideally will have a magnitude response of unity inside this particular frequency, and it will be zero otherwise. For example, let's say we take an arbitrary signal over here just for discussion. So I say that let's suppose this is the frequency response of a particular analog signal having this frequency as omega n and this frequency as minus omega n. But I, let's say, fix my sampling rate omega s, and after fixing this sampling rate, I came to know that maximum allowed frequency is omega c. So definitely I will design an anti-aliasing filter so that it cuts the signal at omega c here and here. So after passing those through this filter, I will get the output signal as this one, roughly. This is minus omega c and this is omega c. So this will be the filtered signal, the output of the anti-aliasing filter, so that now definitely, since maximum frequency is omega c as desired, so now my sampling rate will be exactly 2 times omega c, and such that omega c is equal to omega s divided by 2 at least. So this is the concept of anti-aliasing filter. So after having this discussion, you must now realize that this anti-aliasing filter is mandatory part of almost every digital signal processing system. So the idealized block diagram that we have seen earlier, that was containing only these 3 blocks, but now after this discussion and after understanding the essence of anti-aliasing filter, this AAF will come into the play. And first of all, the continuous time signal will be passed through this anti-aliasing filter having this frequency response ideally, and the output will be XA of t. So this is the output of anti-aliasing filter, and this XA of t will be passed through the subsequent stages of digital signal processing. Now, what is the problem? Usually, not usually, always, these anti-aliasing filters are designed in analog domain, because they will pass continuous time analog signals through these filters. So you must know that designing sharp filters, designing this kind of sharp filters is not a very easy task in analog domain, because in analog domain we have to design filters by using reactive components, by using inductors, by using capacitors, and like that. So by using these reactive combinations, we have to design the filters, and it is not possible for us to design an ideal type of filter, clearly a sharp filter, by using these kind of reactive components. And if we are able to design, that filter will be of a huge size. It cannot be afforded in practical systems. So due to this reason, sharp anti-aliasing filters are difficult to implement in analog domain. So what is the solution? The solution is very interesting. We have to use the digital power of digital processors, for example DSP processors or FPGAs, for the design of anti-aliasing filter. But how? Because we have to pass the analog signal through this filter. So how can we use digital processors? The approach is very interesting. It contains 4 parts actually. What we do, first of all, we use a simple anti-aliasing filter in analog domain that is not very difficult to design. It can have a very large transition region. So you can say that first step is a kind of rough filtering, where we do not want the filter to be very sharp, right? So after that kind of simple anti-aliasing filtering, because the maximum frequency is not our desired one after this rough kind of filtering, definitely it will be greater than the desired one. So due to this greater frequency, we need to have higher sampling rates. So we will perform oversample the signal with sampling rate above Nyquist criteria. I will show you with the help of examples. So now we will sample the signal at a higher sampling rate above the Nyquist criteria. Once we perform oversampling, now the signal is converted into digital domain. Once we have the signal in digital domain, now we will use sharp anti-aliasing filters by using the processing powers of FPGAs and DSPs. There we can design simply very sharp anti-aliasing filters very easily. So anti-aliasing filters will be designed in digital domain, and the digital signal will be passed through these idealistic kind of filters. And after passing through the filter, because we have earlier sampled the signal at a higher sampling rate, so what is the procedure for reducing the sampling rate? If you recall the previous lectures, it was called decimation or downsampling. So now we perform decimation by a factor of m to convert the digital signal back to a sampling rate which was the desired one. So that will be the overall block diagram, and this concept is called oversampled ADC for analog to digital converter. So it is basically the concept of oversampled ADC consisting of 4 stages. So all those 4 points are summarized in this particular block diagram, which says that the input signal xc of t is passed through a simple anti-aliasing filter which can have a very large transition region, and then this anti-aliasing filter output is passed through C to D converter at a higher sampling rate, which is t is equal to 1 over m into pi over omega n. I will show you how it is how this sampling rate is decided. Then we will get x hat of n, which is the sampled signal at a higher sampling rate. Then we pass through this signal to a sharp anti-aliasing filter having cutoff frequency of pi by m, and followed by the downsampling by a factor of m to have the desired signal over here. Now let me explain the same diagram over here with a bit more detail. First of all, we have xc of t, the continuous time signal. This continuous time signal is passed through simple anti-aliasing filter in analog domain to produce the output xa of t. Now we'll pass through this xa of t through C to D converter having sampling rate of capital T, right? Now what is the value of this particular sampling rate? Now since you know that omega s is equal to 2 pi over capital T from the sampling lecture, here capital T becomes 2 pi over omega s. And let's suppose that the maximum, desired frequency is omega n, which means that omega s, as per Nyquist criteria, it must be equal to 2 omega n, right? So it will become from here we will have 2 pi over 2 omega n. So this 2 will be cancelled out. Let's say we call it this t prime, because we have to increase the sampling rate, so we just call it as t prime. So t prime will become pi over omega n. So this is the sampling period as per Nyquist criteria. But since we are talking about oversampled ADC, we need to sample it at a higher sampling rate, which means that we need to have Fs. We need to have Fs is equal to m times Fs prime, where this Fs prime is as per Nyquist criteria, as per Nyquist theorem. So if this is the case, then we can definitely write here as t is equal to t prime divided by m. So by using this particular expression over here, in this expression, we can easily write t is equal to 1 over m pi over omega n. So that was the sampling rate that was mentioned in the slide. It was 1 over m into pi over omega n. So this is the increased sampling rate or reduced sampling period at which we need to perform the oversampling. Now the output will be x hat of n, and it will be passed through a sharp anti-aliasing filter. Sharp anti-aliasing filter in digital domain having cutoff of pi by m. So after passing through this particular filter, we will have x f of n, the filtered output, and then we will perform downsampling by a factor of m to have the desired signal x d of n, and this is the signal whose sampling rate will be Fs dash, right? So this was the required sampling rate. So the complete concept is known as oversampled ADC. Now let us take an example of how this block diagram is traversed if we are given some kind of frequency response. So let's say we have CTFT of a particular continuous time signal as this one. Where this particular frequency is minus omega c, this is omega c, this is minus omega n, and this is omega n with the amplitude of 1. Now, if we are going to sample the actual signal as per Nyquist theorem, we need to have the sampling rate 2 times of omega c, which will be very higher. So we do not want to use this higher sampling rate, but we have to use the sampling rate 2 times of this particular frequency. So first of all, we design a simple anti-aliasing filter, not a filter which is very sharp and just extracts this rectangular spectrum out, but we simply say that we can have a filter like this. So you see, this simple anti-aliasing filter has a very large transition region. It is not very sharp filter. So this kind of filter is very easy to design, relatively easy to design in analog domain. So after passing through this filter, we will get the output of the first stage, which may have a shape like this. It will not affect the actual spectrum. You can say that this particular thing is a noise, or any kind of portion of the spectrum which contains less contribution of the actual spectrum. So it may have a shape like this. After filtering, the amplitude will be reduced on both sides. So roughly it will have a shape like this, where this is again minus omega c, this is minus omega n, this is omega n, and this is omega c on the scale of omega. So it will be xa of j omega, right? So this is the output of the first stage. Now we need to perform sampling, and we have to draw the output of the oversampled ADC. And remember, the sampling period was t is equal to 1 over m pi over omega n. So as you should know that the output of the sampling, we will draw DTFT over here, which is x hat of e raised to power j omega. And what is the main theme to draw the output of the sampler, it will generate multiple copies at integral multiples of 2 pi. So the same thing will be repeated at integral multiples of 2 pi. So first I will draw the copy at 0. And just I have compressed this picture so that I can arrange all the copy, or at least 3 copies in this figure. Let's say this point is 2 pi. So the copy at 2 pi will be like this. This is the copy at 2 pi. Similarly, the copy at minus 2 pi may have a shape like this. So just consider these amplitudes to be, let me draw it again, because the amplitudes will be the same, like this, and the amplitudes will be 1 over capital T, because after the output this is the amplitude. And what will be this point? This is very interesting. This point will be small omega n, because we have drawn DTFT. This point will be minus omega n, and the axis we are using is small omega is equal to capital omega into t. So this omega n will be equal to capital omega n multiplied by capital T, right? Okay. Now, what is the value of this thing? From this particular equation, if you rearrange this, omega n will comes out to be pi over m multiplied by capital T. So if we use this particular equation over here, omega n comes out to be pi over m t multiplied, sorry, it is divided. I made a mistake. Here it is divided by capital T. So let me correct over here, 2 is t and multiplied by capital T. So this t will be cancelled out and you are only left with pi over m. So it means this point is equal to pi over m and this point is equal to minus pi over m. So this is the output of the second stage, which was oversampling. Now the third stage is we will pass this through a sharp anti-aliasing filter having cutoff frequency of pi by m. You see, now we can easily see that if we design an anti-aliasing filter in digital domain having this cutoff frequency, so this is sharp anti-aliasing filter having cutoff frequency of pi by m, and definitely because it is a digital filter, it will have copies over here, it will have copies over here. So the output of this sharp anti-aliasing filter will be like this. This portion which is containing the aliasing will be removed and we are only left with the clean copies, which will have shape like this: pi by m, minus pi by m, and also at integral multiples of 2 pi it will have 2 pi. Here we have minus 2 pi, and the amplitudes will be 1 over capital T. So it is basically xf of e raised to power j omega, which is the output of the filter on the scale of omega is equal to capital omega into t. Now we are only left with the last series, which is downsampling, and downsampling by a factor of m. So if you recall the concept of downsampling, how we can draw the frequency domain plot after the downsampling, the main theme was, the rule of thumb was, we need to expand the spectrum by a factor of m, and we will keep all the copies located at integral multiples of 2 pi. So first of all, the copy at 0, let's say this point is pi and this point is minus pi. So this copy will be expanded by a factor of m, so that this pi by m point will go to pi and this minus pi by m point will go to minus pi. So it will look like this. Similarly, the copy which was located at 2 pi, it will also be scaled. The copy which was located at minus 2 pi, it will also be scaled. And the amplitudes will be 1 over m capital T. So this is the final output in the form of DTFT. So now you can see that since we have used the concept of oversampled ADC, we have got two main advantages. The first advantage that we got is we have removed the aliased components shown in this particular diagram. This is the distorted portion, and secondly, we have got the signal at the desired sampling rate, which is fs dash, and this particular signal is sampled at fs dash, which is equal to fs divided by capital M, which was the required sampling rate, right? Or you can write it as 1 over M capital T. And what was capital T? If you just put the value of capital T, it was 1 over M pi over omega n. So this is cancelled out, and you are only left with omega n divided by pi, which is the desired sampling frequency, which is exactly 2 times the Nyquist frequency. So you can always change this fs dash into omega s dash by multiplying with a factor of 2 pi. So it will be 2 pi into omega n divided by pi. This pi will be cancelled out, and you are left with omega s dash is equal to 2 times omega n, which was the desired low sampling rate. So by effectively nullifying the aliasing, we have got the final discrete time sequence sampled at the desired low sampling rate. So that's all for this lecture. Thank you very much.